uh, and also thank you to everyone for your interest, for taking lunchtime for this webinar. Um, and yes, like I said, I was have been for a long time already involved in developing the scope, the model scope. When we started, well, first of all, we didn't know that after 2 years working on it, we decided for the name scope, but we also didn't know at that time who will be using it and for what purpose. And it's nice that and now we have seen a few different applications of this model, and in that respect, it's nice to show it to everyone and see whether it can be useful for your own work as well. So in the, especially in the Senseco network, which is about remote sensing of vegetation and bridging scales and so on, and working with good data. So I uh, don't know in if you look at the audience that some of you might have used scope and others for others it might be completely new. So since we have a 1 hour meeting now, my idea is for most of it to get inspired. So what I want to show you is some things that just might give you some ideas. Then also give you already an idea how to use it and where to get it to it. So a bit on getting involved and getting access to the code and see how it works. And even develop, because this is not just my idea. It is many people have been contributing, and I also think that it's very good that people start to develop it. So it's basically 3 levels, and in 1 hour it's probably too much to go directly to the last step, but for sure we can get all inspired. So the basically the motivation why scope. Let me show you what the abbreviation means. It's soil canopy observation of photosynthesis and energy fluxes. So it is about, part is about photosynthesis, about what plants are doing, and part is about energy. And you see also soil and canopy is the vegetation canopy. So basically what we know is that we have solar energy, and we know quite accurately how much it is, how much energy the Earth receives, and then a lot is happening with that energy. So it drives the processes on Earth, and eventually also our own energy use. And you see these airplanes. So a lot of energy that arrives at Earth, and it has been accumulated as photosynthesis that is also now used as a fossil fuel. So we also know that plants have played a very important role in the climate, and we know, of course, everyone knows the CO2 fixation by plants, but there is more. Plants also um, uh, transpire, and they take water from deep and transport into the deep into the continent. So the fact that we have rainfall very far from the ocean is also contributed by plants who develop soils and who extract the water. So in many aspects, plants are vital. And now in this time, we see climate change. We see, of course, emission of CO2, but also land cover changes. And it is important to understand that how that works. So what I like to do is use an analogy to how a watermill. So if you take a watermill that uses energy from gravitational energy from water to drive the thing. So you can also see photons from the sun as driving energy, driving processes, biophysical processes. And what we wanted to do is to make that link between photons and biophysical processes explicit, quantitative, and physically based. Because this can help us to use also satellite data, because with satellite data we mostly measure photons. So that is basically the idea why scope is there and why we started working on that. Then if you look at Senseco, it's all about scale, satellite data, and eco-physiological processes and skills. And then I also have another question to you, if to think about. Let me see if it wants to move to the next. Yes. So the question is, do you use all the 4 dimensions of remote sensing? So we have tons of remote sensing data nowadays. So in this Senseco, it is a lot is about Sentinel-2 and 3 and the coming mission Flex. But there are many satellite data. How do we use that? Do we fully exploit these data? So the 4 dimensions of remote sensing, any idea what are the dimensions of remote sensing data? Yeah, so actually we can differentiate space and time, of course. So we have spatial information, we have time series, so we have data in distributed in time intervals, space intervals, time intervals, spectral intervals. So the electromagnetic spectrum provides information in different bands. And finally, we have angular information, so the observation and illumination direction. So these are 4 pieces of information that somehow we want to exploit and bring together. So scope is one way where we have been thinking about how to do that. So it's not the only way, of course, but I can show you some examples, some ideas of that we have been looking at how to make best use of the information, especially if you have many satellite data, different from different sensors, you will have difference in spatial temporal spectral resolution and observation geometry. And if you want to use this information combined, you need somehow to bring this data together. And models can help with this. So that is also a context of behind the ideas of scope. So basically what you have is satellite data. You see here the Sentinel-2 that provide you measurements, observations in different spectral bands. So maybe not continuously the spectrum like here, but snap parts of the spectrum. And what we want to know is what is going on in the vegetation. What is the water flux? What is the carboxylation? So the fixation of carbon as in biomass, and how is this energy used? Is the vegetation functioning optimally? Is there stress? Are there diseases? So these aspects is what we actually want to know. So the radiation that we measure is not the final goal. We want to know a bit more. So we need to go beyond this, um, beyond the direct measurement. So the main thing, if you look also, if you go and unpack the code of scope, what you see is a lot of radiative transfer. So you see the biggest part of the model code is radiative transfer. So what is radiative transfer? That follows basically the photons from the sun to the observer via the surface, so via the canopy and the soil. So there are several processes involved, like absorption, but also scattering, that can be reflectance, transmittance, but there is also emission of radiation of photons within the vegetation. So that's also part of the radiative transfer problem. So we try to understand where do the photons come from and what happens on their way on the path from the sun to the observer, what kind of processes they drive and where exactly. So if you look inside scope, it has many components, and some components you can use standalone, so not as inside scope, but as part of as an independent module. So you will see radiative transfer for the leaf and also among leaves and soil. So the first one, it looks at what is happening after light has hit plant leaf, what goes on inside. And here there is also analogies from other disciplines, because this field of science is also done in just paper radiative transfer, also in paint and so on. Probably you can find some things in restoration of old paintings and so on. So that is a nice field of expertise that to develop. And the other one is the radiative transfer inside the whole canopy. I will talk about that. But apart from radiative transfer, there is something more. So once a photon is absorbed, then it ceases to exist. So radiative transfer models, they stop there. So they don't consider energy after it's been absorbed. But the idea of scope is to go further. So the energy has not disappeared. The photon does not exist anymore, but the energy is still there. So where does the energy go? What does it do? So some a part of the model, and we are still in the beginning of doing that work. So even though I've been working for years on it, uh, we are, I still have the feeling that we are just starting this. So what actually happens is when the photons hit are in the pigment bed of the chlorophyll complexes, then something is happening. So photochemistry, of course, is the main process, but also other processes take place that make produce heat and so evaporate water. So what happens to the energy after absorption is part of the model. So if you look then at an energy budget, here a simulation of scope for a clear sky day. So what happens to the solar diffuse and direct solar radiation that reaches the surface? Then you will see different components. One part that is reflected by the surface. Then there is also emission by the vegetation itself. Most of that is thermal radiation. So radiation around 10 micrometers of wavelength, and that is emitted as heat to the atmosphere. Then there is also a sensible heat flux. Sensible heat flux is not radiation. It is simply heat that is transported with the with a medium, with the air in this case. So air is heated up and the air moves physically from A to B. It moves from the surface into the atmosphere. So this is the big. So wind carries this energy from the vegetation away. Then there is latent heat fluxes. So latent heat fluxes, this is the phase change of water, basically. So water that evaporates, it costs 2.5 million joules to evaporate 1 liter of water. So that energy that is absorbed by the vegetation can be used for this process, transforming liquid water into gas, but also ice into water, ice into vapor. So all these phase changes are included, and the other way around as well. So the dew formation, water condensation on site on the leaves is another component. Finally, there is heat storage. During the day, heat is stored inside the vegetation, also in the soil, and that heat is released at night again when especially during clear sky nights when the radiation, uh, uh, when there is still outgoing radiation is lost, and that is compensated by heat coming from deeper in the ground. And finally, there are also chemical reactions. So photosynthesis also extracts energy. So, but if you look at it in number of watts per square meter, this is still a relatively minor term. So by combining this inside scope, this is combined. So the radiative transfer is calculated, but also these different phases of the radiation after absorption. And by doing so, it's possible to simulate the temperature of the vegetation and of the individual leaves and soil. And that makes it possible to simulate also how much radiation is emitted. And here you can see on the left a panel, you see a simulation of leaf reflectors and transmittance for two leaves of different chlorophyll content. So that is what happens to incoming radiation, to solar irradiance, what the leaf does with it. On the right side, you see emitted radiation by a canopy. So this is produced within the vegetation itself. And then the part on the right panel, you see around 700 68 to 815 nanometer, so it is 0.7 micrometer. You see a peak there, and that is the fluorescence emission at different depths. At different depths inside the vegetation canopy, from the soil to the top of the canopy. So you see how much fluorescence is emitted. This is one byproduct of the photosynthesis, the fluorescence emission of photons. And then on the right, further to the right, you see the thermal range, and there you see emission of thermal radiation also at different depths inside the canopy at the bottom and the top of the canopy. So this kind of simulation is possible once you have treated the whole energy budget. And that can be useful for thermal remote sensing. Here you see some of the work that's of a former PhD student, Joris Timmermans, who was heavily involved in the development of the scope model. And now you see on the right side, you see thermal images. So it is the long wave radiation measured over a full diurnal cycle. And you see big temperature differences there. So the soil, this is a vineyard, so the soil gets very hot while the vegetation is still cool. So the vegetation is cool because it is windy there. So the wind is in good contact with the leaves. That takes away the heat, but also due to the latent heat. So the transpiration by the leaves, transpiration of water keeps them cool. So such a simulation can give you the full spectrum. So both the reflected and the emitted radiation during the day. So you can see how much and is emitted at what wavelength the whole vegetation plus soil combined. But because you have differences in temperature between the soil on the one hand and the vegetation on the other hand, and you saw also differences among leaves, sunlit and shaded leaves, you also get a different directionality of the measurement. So depending on what angle you look at it, at the vegetation, you will see a different radiometric temperature. So one of the studies that have been done with scope is to understand this directionality of the thermal measurement in preparation of possible satellite missions for this purpose. So in this diagram, you see observations from different angle. In the left panel, you see observations, and then the next one that looks a bit more smooth. In the middle, you see simulations of what the temperature variation is when looking at different angles to the vegetation. So this is a radial plot. So if you look in the center, that means that you look vertically down to the vegetation, and the further you go away, these rings out, it looks more from an oblique angle. And then the phase angle, so that is the along on the position on one of these circles, it is the azimuth angle. So how you look at it with respect to the direction of the sun. You can also take a cross section through the so-called principal plane, that is the direction of the sun. So you look from top to bottom through this diagram, and you can see the temperatures, the temperature differences that occur in with viewing angle. So in this you can do for thermal, but also for fluorescence. So that gives you an idea of how the fluorescence measurement depends on the viewing angle. Now with scope, we can also look inside the vegetation. So we can go in different depths below and above the vegetation and see what is happening. So the key questions there are: what is the illumination inside the vegetation? Not only the intensity, but also the spectral composition. So we call that the light quality. That aspect you can see in these bottom graphs here. So you see spectra with, as a function of wavelength, at different depths from top to bottom inside the vegetation. And then you see the downwelling and upwelling diffuse radiation inside the vegetation. So there are differences between understory and overstory in illumination intensity and spectral shape. So what we can also study is how much is absorbed and where is it absorbed. So where are the sunlit leaves and how much do they receive? So if you do that as a vertical profile, you get what you see here in the top right. You see from bottom to top, you see the amount of photosynthetic active radiation, so between 400 and 700 nanometers of wavelength, how much is absorbed. The final question you can ask is what is the consequence of this for the temperature distribution? Temperature is also an important aspect of the microclimate in the system, especially for transpiration. Now, scope has also been used a lot in the Fluorescence Explorer satellite mission FLEX as a study, and fluorescence is a technique that has been used already for a long time, actually more than a century, to investigate aspects of photosynthesis of plants. But those techniques at that in the beginning time, this was all measurements on chlorophyll or individual leaves, so on a very small scale with active light. So when you measure fluorescence with a satellite from space, you measure at completely different scale. So then if you want to use that knowledge from fluorescence from the leaf and you want to apply it in such a setting of satellite, you do need scaling. Scaling of the processes and scaling, bridging the scale of measurement and bridging the scale of the process. So especially in this satellite mission, it has become clear how important the scaling issues are in linking processes on scales. And actually the picture of the ESA picture of the FLEX mission makes that also clear. If you look at the picture on the right, you see there from within leaf scale all the way to the landscape scale in one figure. So how does that work in scope? So like I said, this is not only my work, it's actually the work of many people who have contributed and being very lucky to work with them and to learn from them. And basically here I try to sketch in two axes. So from left to right is the linking scales, and from top to bottom is linking processes. So the scope treats the leaf, has one component for the leaf and one component for the whole vegetation stand. It also links the radiative transfer that's in the top to the physiology and the micrometeorology, which is in the bottom of this diagram. And there you also see the people who have contributed there to this. So the flashback model you might have heard is a leaf model. And then in scope has a number of Canopy radiative transfer models. They start with RTM, radiative transfer model, and then there is a small letter saying what part of the spectrum we talk about, or what kind of, if we talk about incident radiation from the sun, that's done with RTM. We also have RTMT for thermal, RTMF for fluorescence, and there's one RTMZ, which I will in this presentation not cover. Then we also have a soil reflectance model, brightness, shape, moisture, BSM model, and then some routines for energy balance and aerodynamic resistance, which is more micrometeorology. And on the leaf, we also have the biochemical model for fluorescence and photosynthesis, which is mainly coming from Joe Berry in this figure, who has done a lot of this work for many years. Now is some information about the history of the model. So this is a slide that is from a presentation from a paper by Gina Mohammed et al. From last year, and that talks about the history of fluorescence research, and scope was also mentioned there. Here you can see that actually scope uses, builds upon, and uses other models, basically some knowledge from photosynthesis, some from radiative transfer in leaves and canopy, and also trying to link with land surface models. That is more an application of scope where people are trying to link it with more global land surface models. there is a complex diagram. What I want to say with this diagram is that scope has a number of sub models that you can also use as a model. So some of them have been published as a separate paper, so that's a model. But in scope, they are connected. So if you run scope, it actually calls a number of those functions are as separate submodels. But it's also interesting to look at one of them and try to develop one part. For example, I said mentioned the leaf model, FluxPack, or the soil reflectance model, BSM. And here you can see in this technical diagram how they are connected and how they work together and which are the input and output. Input from one component that goes into the other component, into the other part of the model, and eventually leading to model output. So I can briefly touch a few of these aspects again without going into detail what these models do. So the FluxPack, many of you might also know Prospect. A FluxPack is very similar to Prospect. Prospect is meant to simulate the reflectance and transmittance of a leaf, depending on the chemical composition of the leaf. It's of course a very much simplified version of reality, so a very simplified version of what happens inside the leaf, but sufficient to explain the measurements. And what FluxPack does is adding emitted radiation and fluorescence to this model. So the reflectance and transmittance, they depend on specific absorption coefficients of different pigments. And the fluorescence emission has an analogy, but it depends on the specific emission of fluorescence by chlorophyll. Together with the scattering and reabsorption within the vegetation, this will produce also a fluorescence on two sides of the leaf. So we call that the forward and the backward fluorescence. So forward is the same direction as the illumination, so it's same also as transmittance. And backward is in the same direction as reflectance, so the opposite direction where the illumination comes from. So these spectral shapes of fluorescence are simulated in addition to reflectance and transmittance in an absorption, as you also have in Prospect. Now then the Canopy radiative transfer uses a so-called four-stream radiative transfer approach. So four-stream, it refers to the direction of the radiation. So one of the directions is the solar illumination direction, and the other direction is the observation, is how you're looking at it. Then there are two more fluxes, and these are the diffuse ones. So the diffuse radiation doesn't have a specific direction; it comes from all directions. There we differentiate two half hemispheres. So the one that is oriented in the downward direction, that goes gradually down, and the other one that goes up. So in total, that gives you four directions. And from this, we also can have from the diffuse and direct and observation, we can have four combination of different reflectance factors. So that is the solar that is reflected in as diffuse, the solar that is reflected in observation direction, diffuse reflected in as a diffuse radiation, and diffuse radiation reflected in observation direction. So these components you need if you want to simulate the satellite signal, and if you want to couple the surface to the atmosphere. So you want to model the scope in combination with an atmospheric model. So if you look how that is done, I mentioned this because the concept has changed in the last 2 years or so, because the work of Pai Ji Yang, he has made, compared to the first version of scope, he has made a slightly different approach to solve this issue, to solve the differential equations of radiative transfer. So basically, you can combine different layers. So the soil, vegetation on top, and atmosphere, or soil and different layers of vegetation on top of each other. And the technique that we use is stacking layers, so stack layer upon layer and see what is the effect of combining two layers on top of each other. And that gives you optical properties of the whole system. And then radiative fluxes are done by peeling. So once you have done the stacking, you know what the optical properties are of the different layers and the combination of layers. You go back from top to bottom and you see what radiation does as it enters the vegetation. So stacking and peeling is the technique, and that can be also be done with sublayers. So you have a whole vegetation layer, and you differentiate different sublayers, small layers, and you see what happens inside. So an important, interesting aspect is, of course, leaf orientations in that respect, because they also determine the optical properties of the layer. So if you have a vegetation layer, it is the leaf, the orientation, and the density of the leaves. And here you can see from a very nice American study, you can see the movement of diurnal movement of leaves, and that has of course, a physiological meaning why these leaves move. So in scope, this is also parameterized. So in terms of quantifying what is the orientation, horizontal, vertical, and then different distributions. Here you see an example. Spherical distribution would mean that if you take the leaves, then they would fit nicely on a circle. If you take the distribution of all those orientations that occur. And I'm mentioning this because sometimes I get questions from users about this what does it mean, the leaf orientation? So basically, if you would sort the leaves and you make a cumulative distribution function of these angles of the leaf, then you can describe the cumulative distribution function with a line, with a fit. And that fitted line has two parameters, and one parameter is LEDF A and the other one is LEDF B. And one says, what is the preferred direction? Is it more vertical like graphs? Is it more horizontal oriented or something in between? And then the LEDF B says, is it bimodal? So it can be that there is a preference for both horizontal and vertical, but not in between. And this gives you a full range of different lines of this cumulative distribution function. You can find that in the PhD thesis of Wout Verhoef. But here you see some graphical representation. So uniform planets, all these, how they on the horizontal axis LEDF A, on vertical axis LEDF B, how these distributions, how you can quantify this. So fluorescence, I just touched it briefly in view of time, but it has been used a lot by users of scope. And because of the radiative trends of fluorescence, scope can differentiate where it comes from. Does it come from sunlit leaves? Does it come from shaded leaves? Or is it actually fluorescence that has been scattered multiple times, maybe scattered by the soil or scattered by other leaves towards the center? And because the radiative transfer is stimulating this, we can also differentiate those sources and see what is the effect of structure of the vegetation on fluorescence, or in an analogy, thermal radiation. Now then, what you scope is a so-called forward model. So it starts from vegetation, and then it does a simulation of satellite signals or spectra. But in many applications, you want the other way around, because you have satellite data, UAV data, or field data, spectral data, and you want to know something about the vegetation. It means you have to go inverse. You have to go backwards from the satellite data to the vegetation. You cannot just run scope in this way. So you cannot give as an input a spectrum and then let scope tell you what vegetation it is. That is an inverse problem. In first problem, we have a lot of expertise in Senseco for other people who can educate how to do that, and who have lots of experience in best technique, best practice of doing this, what works, what does not work. So I'm not touching it in detail, just mentioning that this is a possibility to use scope in this way, in an inverse mode. It has many applications, and it requires also some expertise to do that. Now I give you just a few examples of how scope has been used. So one idea how you can use it, because it's a relatively detailed radiative transfer concept. If you have an idea, smart idea, and vegetation index, or a theory, or an hypothesis, of course you need to test that hypothesis in the laboratory, in the field. But you can already do an in silico experiment. So you can use scope to test whether the assumption that you make, your idea, whether somehow it works. It's not the proof because our model scope is not the truth, but it can help you already as a first step to test your approach, to test the effect of the assumptions that you make. So this is one way in which, in a number of papers, one way in which scope has been used. Another example is Marco Celesti, is where you have field spectral measurement time series, and you try to retrieve information about the vegetation, and you see how this vegetation is changing over time in an experiment. And this experiment was about reflectance and fluorescence, and seeing how chlorophyll changes when you do a treatment with certain pesticide or herbicide, sorry, on the vegetation, and seeing how that influences the photochemistry using this fluorescence measurement. You can also go for satellite data. So in this case, it is also inverse modeling, so retrieval. But then you may need other techniques for mapping and for making big large number of computation for computation time. So then you can try and retrieve here photosynthesis, for example, from the satellite images. Now then, how to find it? Huh? So I try to give you a few. I will give you a few resources where you can start reading reading about scope or get some more ideas. So one thing is our website. At the moment, the path to find to the website is very long. So what I recommend is just to use your search engine, your Google or so, to type scope ITC, something like this, scope utwente, and to find the website because the link is a bit long. But on that website, we try to give complete and up-to-date information about papers that have been published with scope, if there is a new development, and also a short description with links what it is all about. Then there is the Git repository. So in the Git repository, you'll find the code. To download this is quite easy. So if you go to this location, you can click on code, and there you can click download or clone. If you're using Git yourself, you can clone it also, and then you can work from there. So it depends how you use it. But downloading will give you the full code plus also some input output data, so that it should already work directly, and then you can start modifying and using. And then there is read the docs. The read the docs, I think that in the slide the exact web address is behind the picture by mistake, so you can't see at this moment the link to read the docs. Again, you can use Google to find the read the docs scope, or I can give you the link later on in the chat, where you can read more detail what each variable means and how it's used in the model. So it gives you a lot of more background about scope. And finally, then how to run scope. So it is all written in MATLAB at this moment. So there we have discussions how to translate it to other languages, because of course it's preferred to have a software that is really, if it's really open access, then the software should also be publicly available, but this is not the case. MATLAB is a licensed software, so many universities have MATLAB license, but it's not everywhere. So what we have been doing is also supply an executable for scope, which you can run without having MATLAB. But this executable is not yet available for scope 2.0, and this will be a matter of short time to make it available. You can always send me a message that you need it. Otherwise, you have to use MATLAB to run it. And then you can change input, output, file names, and etc. to change input to scope and see what it does, and use different simulation options. There is a folder where all output is saved, stored, Here is just an example of a number of output variables. These are the radiometric variables that are saved with the name of with the file name and unit and the description of what it is. Apart from this, you also have the energy balance and some vegetation parameters that are provided as output. The documentation in terms of written papers. So there was a main publication was in 2009 in EGU Biogeosciences. So we also have Scope 2.0, which is a major update of the model with new features. And that paper is not yet accepted. It is in review at Geoscience Model Development. But the good thing is that this is an open review process, so you can see the preprint, you can download it, and you can even comment on it if you want. So there you can also post questions in the GitHub repository or by email. So I give you the two email addresses here from myself and Igor, whom you might know, Igor Prikazuk, who is also doing a lot for developing of the scope model at the moment. So then we hope to help you further if you want to use it, or just give feedback if you think you found a bug, which is possible, or if you find some functionality that you want to have for an application. For any of these questions, you can contact me. And with that, I think that I have finished for my part the presentation, and I want to allow sufficient time for you to ask questions or to put them in the chat, and I'm happy to discuss them with you.